So, hello everyone, welcome to lecture 34. So, we were looking at surfaces, we looked at what surface energy is. Surface energy comes because of dangling bonds is what we said, but so very basic idea of surface energy is you do not even need to think of bonds. If I take a any material and break it into two, I have to spend some energy. The minimum amount of energy I spend divided by 2 times the area that I form. That is a good way of understanding what surface energy is, right. So, surfaces, to create surfaces would require some energy, and that is so that goes in as surface energy, that adds up to the bulk free energy, right. So, by all the bulk free energy that we calculated, and so when the consequence of having a surface energy, we looked at the case of isotropic surface energies for liquids, for example, or amorphous solids or whatever it is, right. So, so in case of materials having isotropic surfaces or isotropic surface energies, so as soon as so you nanocrystallize the materials, the shape that these surface energy will dictate, surface energy minimization will dictate is a sphere, right. And these spheres also, you keep making these spheres smaller and smaller and smaller. The area to volume keeps increasing, but that is also increasing the surface, that is what people loosely call it as surface area is increasing, but that is also equivalent to increasing the Young Laplace internal pressure inside these solids, right. So, we have seen examples where this pressure itself was enough to actually convert a high volume phase into low volume phase in a material called hafnium dioxide. Okay. So, nanostructuring is important. I mean, so we can also while growing thin films, we can create enough surfaces, right, to nanostructure materials and grow them in different phases than what is conventionally achieved, right. So, especially when you make them nanoscopic, you can create enough surfaces, right. So, it does not need to be only spheres, right. So, but this is the idea of making things nanoscopic. You create enough surfaces that the first effect that kicks in is the Young Laplace pressure, and so because of effects like the Young Laplace pressure, you can do things that are otherwise not doable in bulk. Okay. Now, so let us come back to this, and then so we discuss the differences between what surface energy is and surface tension is. Surface energy is exists always, right. So, when two surfaces are there should always be surface energy, but surface tension comes up as a function of time when these bonds, the surface bonds sort of reorganize, flow in, the atoms flow in, make dislocations and things like that, so and make defects, and that creates some internal pressure, just like in a bubble, in a gas bubble or in a liquid bubble. So if I apply some so there is always some internal pressure which we derived, right. Okay. And then the pressure, the idea of surface tension, surface pressure, and then surface energy become equivalent. All right. Okay. So now let us go more atomistic. Okay. And by atomistic, what I mean is the fundamental most important crystal that we said for this course is what is called Kossel crystal. Let us look at Kossel crystal. But before that, so I have a material A, I make two surfaces A, right. So, the surface so and then I am going to say that the Miller indices of these planes are HKL. Right. So, it is cleaved about an HKL plane, right. So, HKL is some parallel set of planes, but this is being cleaved about one such HKL plane. Okay. So, then if I ask you the question, what is the surface energy of the HKL plane, right. So, all HKL should have the same surface energy, that is the total energy required to break it into two divided by 2 times the area that I have created, right. So, area I am going to write it as sigma HKL, which is the area of the plane, and this capital psi will be the total energy, and this gamma is the specific surface energy. Okay. Okay. Now let us go back to Kossel crystal. In a Kossel crystal, so I have atoms which are all arranged like this. I will do the same experiment. So, now I am going to create a surface here, right. So, let me look at it from the perspective of one atom, right. So, I am going to how much is the energy. So, I want to calculate what gamma 100 is, these are the 100 planes. Okay. So, I cut it here, I am cutting these bonds, how many bonds am I cutting, that is the question, right. So, so I am cutting one nearest neighbor bond, right. So, that is sigma 1 nearest neighbor bond, sigma 1, right. So, that is the first nearest neighbor. I am cutting, there is 1 here, there is 2 here, and there will be 2 more on, so on this side, right. So, this is a 2-dimensional surface, right. So, there are 2 on this side and 2 more on the other side, right. So, I am cutting 4 second nearest neighbor bonds, right. So, this is the nearest neighbor, right. So, I am breaking that spring. So, there is some energy that I expend to do that, that is the bond energy essentially, right. But the second nearest neighbors also start interacting, right. So, it is not just the first nearest neighbors that are interacting, the second nearest neighbors are also interacting. So, I am cutting that also. Okay. So, that those bonds are also now gone. So, now there is some extra energy coming from the second nearest neighbors. Okay. And then I am also cutting third nearest neighbors, there will be 4 third nearest neighbors and so on and so forth. Okay. Divided by what is the area? The area is just the area taken by this atom, right. So, the area taken by this atom is nothing but the lattice parameter is A, this is a Cauchy crystal, A square, very simple, right. So, A is the bond length, this direction, and A square is the area of this bond. Okay. So, this is how I can just calculate, so I can also go for sigma 4, sigma psi 4, psi 5 and other things, but you will already realize that psi 2 is about 10% of psi 1 and psi 3 is about 10% of psi 2. Okay. So, the bond energies they just die down as so the bond energy of the nearest neighbor is something large, then it falls to 10% for this is nearest neighbor, this is second nearest neighbor, this is bond energy versus a distance from the atom, right. So, this is the atom. And then third nearest neighbor is going to fall down even 10 more percent, right. So, fourth nearest neighbor is almost 0. Okay. So, all the energy sort of dies down by 3 nearest neighbors, all the bond energies, right. So, this atom is not interacting really with the fourth atom from in the sequence, right. So, that interaction is very minimal. It can interact with first atom very strongly, right. It can interact with second nearest neighbor reasonably strongly, and then the third nearest neighbor also weakly. So, we are able to take up to the third nearest neighbor and fourth nearest neighbor and all we will just ignore. Okay. Now, the question is that is why we talk about coordination number. Coordination number is the number of nearest neighbors, right, because the bonding always is strongest with the nearest neighbors. I can just take the nearest neighbors, that is also fine, right. So, but this will just make it more accurate. If I am taking the second nearest neighbor, third nearest neighbor, the calculations become a bit more accurate of surface energies. Okay. So, this is how I can calculate the surface energy of gamma 100 if I know the bond strengths, or if I know the first nearest neighbor interaction, second nearest neighbor interaction, third nearest neighbor interaction and so on. Okay. All right. So, now the question is, can I calculate what gamma 110 is? So, for 110 I need to so I am going to cut it like this, but this is just going to go this is a plane that is just going to go in the 001 direction, right. So, in this direction it is still 001, but in this direction it is going to be 110. Okay. So, that is a 110 plane in some sense, right. So, that plane is just going to go like this. Okay. So, that is the cut I am going to make, right. So, now how many nearest neighbors I am cutting, the first nearest neighbors am I cutting, right. So, with respect to this atom I am cutting 2 I would guess, right. So, there will be 1 here and 1 here, right. So, these 2 nearest neighbors is something that I am cutting, 2 psi 1, plus you can actually calculate along the 110 cut how many second nearest neighbors are there, 6 psi 2 plus 4 psi 3. You can actually visualize these things, right. So, look at this software called Vesta, try to put these atoms in 3 dimension and then cut it along a cut plane and see how many the first nearest neighbors, second nearest neighbors, third nearest neighbors are cut, right, divided by 2 times, actually this is 2a square because it is 2 sigma, right. So, not just a square. Okay. 2 times what do we have? We have so along this direction this atom has a square root 2b, a square root 2a, right, and along the other direction, along the out of plane or in plane, that has an a, the area of that is a, right. So, square root 2a square. So, essentially it is 2 psi 1 plus 6 psi 2 plus 4 psi 3 divided by 2 root 2 a square. Okay. So, that is the gamma 1 1 0. Similarly, I can also calculate gamma 1 1 1, but you can actually see here very easily that so gamma 1 sorry psi 1 is the most important thing, right. So, this scales as psi 1 by 2, this scales as psi 1 by square root 2, right. And the third so gamma, so you can actually see that gamma 1 0 0 is less than gamma 1 1 0 is less than gamma 1 1 1 is less than, and so on and so forth, right. So, this is true of what is called a simple cubic structure, or in our case we just call it a causal crystal, right. Gamma 1 0 0 has the minimum surface energy, right. So, out of all the planes that I have crystallograph, so now I am translating surface energies into the language of crystallographic planes, right. So, out of all the surfaces I have, the 1 0 0 surface has the minimum surface energy. Okay. Now, if I do the same analysis for FCC crystals, I will see that gamma 1 1 1 has the least surface energy. Gamma 1 1 1 is less than so this will be, I think 1 1 0 will come next, and so on and so forth. So, this has the least surface energy. Okay. Now, if I and similarly if I look at so essentially the planes with the least surface energy have the highest planar density of atoms. Okay, that sounds a bit counterintuitive. If I have lot of density of atoms, if I cut them into 2 or something, then I have to spend more energy, right. Ideally, if I am sparsely populated, then I can cut it easily because everything is an atom. But if atoms are very densely populated and I cut it, the cut should be hard because so every atom is interacting with every other atom, right. So, this plane I am saying has it is very closely packed plane, right. So, with a lot of atomic density, right. Okay, so this is a very closely packed plane, highest planar density of atoms, and that is called close packing. Okay, does not need to be always closely packed, but yeah. So, in FCC 111 is the closest packed plane. In simple cube 100 has the highest density. It is not close packed, but it has the highest density. Okay. So, if I make surfaces out of this, right, then it feels as if I should expend more energy, but somehow I can see that gamma 100 is the least, gamma 111 is the least in FCC crystals, and so on and so forth. Okay. So, the fix is simple because we typically think that we have to cut surfaces in this direction, right. So, whenever I give this problem to as an interview problem, people start cutting it in this direction, and that is not correct. Okay. So, what you are doing is you are actually cutting perpendicular to these things, right. So, there are other bonds coming out, right, but in plane, right. So, if my atom has let us say the coordination number of an atom is 6, right, and in the plane itself I am already bonding to 5 atoms, or so 4 atoms or whatever. So, out of plane I should only bond to 1 atom on this side, 1 atom on that side, right. But in plane if I am just bonding to 3 atoms, then out of plane I should bond to 2 atoms on the top, 1 atom in the bottom, or something like that, right. So, the number of atoms bound out of plane, that is what is important. So, perpendicular to this plane, right. So, the number of atoms bound perpendicular to the close packed plane is the least, right, and that is why the surface energy, or so once these bonds are broken, to create a surface, least amount of energy is expended. And so, the surface energy of close packed planes is the least in any crystal system. Okay. So, now this crystal system FCC, BCC, all these things you can look at my other course, where I talk at length about symmetry, crystal structures, Bravais lattices and other things. But so for now, if you understand FCC simple cubic, that is fine, otherwise just read it up a bit. Okay. So, what are these crystal structures and things like that. Okay. All right. So, now okay. So, before we move on a bit more, that is fine, but so if I take a wafer, right. So, a wafer of silicon, a wafer of silicon is 500 micrometer in thickness, and then you see that there is a face, this is a very well polished face, okay, very smooth surface, and so this is oriented about so I call this a 100 silicon, means this is oriented about 100 direction or 001 direction. Okay. So, this is called so the wafer in the plan view will look somewhat like this. Okay. So, this is a 100 plane, right, or the direction perpendicular to that is a 001 direction, oh sorry 100 direction. Okay. Now, it is not just silicon, I can have many other single crystalline substrates, right. So, I can have single crystalline substrates oriented along various directions. Crystallographic directions, right. Now, okay, so if this is 100, I call this a 100 oriented silicon, but if this is so 111, what is preventing me from creating 111 oriented silicons, I will call this a 111 oriented silicon. Okay. Similarly, for any substrate I can have the termination, right. So, it depends on where I cut this substrate, right. So, if I cut it like this, I have a different plane, if I cut it like this, I have a different plane, if I cut it at 45 degrees, I have a different plane, or if I cut it like this, I have a different plane. So, the orientations become different, the surface orientations become different. Okay. So, I can have 100 oriented, 111 oriented, 110 oriented crystals, right, which is essentially saying what is the normal to the surface, what people call as plane normal. Okay, and that will be the so the reciprocal lattice vector of 110. Okay, all right. So, okay. Now, typically when I buy substrates, right, when I buy single crystals, you can make single crystals, okay, buy or make single crystals. Okay. So, let us say I am growing an ingot of silicon through this Czechoslovakia process, right, and eventually I have to cut it into various wafers. Okay. Right. Similarly, I grow any other crystal, right. So, I grow it as an ingot, right. So, ingot of any crystal, and eventually I cut it, which is eventually cut. alright. Now this cut, right, in these wafers, right, I am going to show you later on that, you know, so although, and then this cut gives me a surface, right. So this is the wafer and this is telling me I cut it, I polish it and so on and so forth, right. So this is the 100 phase, okay. So this is 100 oriented crystal, let us say, okay. So the surface that is pointing out to the atmosphere is a 100 surface, it is a single crystalline surface, okay. But you will see that, you know, this 100 surface can never be parallelly cut, right. So if it is totally parallelly cut, that is called a singular surface, right. So throughout, you know, so I just have a very nice 100 surface that is nicely cut at 90 degrees with respect to this, right. So the ingot is growing like this is the 001 direction, right, and then I cut it exactly at 90 degrees to 001 direction, I get what is called a singular surface, okay. Singular surface means it is a 100 surface throughout, you know, the entirety of the single crystal, okay, that is a singular surface. Now singular surface by definition, this is a very unstable surface, and I am going to prove will come in 2 to 3 classes from now, okay. So these are very unstable surfaces. So typically what we get are not singular surfaces. I have an ingot, I cut it, but I cut it at some angle, right. So this is called, you know, so it is not exactly perpendicular, but it is at some angle, and this angle is called miscut angle, okay. Now miscut surfaces are more stable surfaces, right. So I am going to show that why that is the case. And also if you want to cut exactly at 90 degrees, it is not going to be 90 degrees everywhere on the sample, there will be some little deviations, right. I will get 90 plus or minus 0.01 degrees, and that plus or minus 0.10 degree 0.01 degree cut gives me a miscut, okay. So there is some miscut angle always, and that miscut angle can be 0.01 degree, that miscut angle can be 0.1 degree, it can be 1 degree. If I take a bad substrate, it can also be 5 degrees, right. So this is bad, I do not want to grow on substrates which are 5 degree miscut angle, but you know, so the miscut otherwise is useful, okay. Okay, so now once I miscut it, okay, and I ask you the question, this is my 001 direction, right, and I am asking you the question, what are the planes that are not at 90 degrees, because the planes which are at 90 degrees to 001 plane are 001 direction are 001 planes, right. So that is how it works in a cubic system, right. Let us just assume simple, again causal crystals, back to causal crystals, cubic crystals, okay. But the planes that are at something like, you know, 89.9 you know 9 degrees, okay, that is 0.1 degree miscut to the 001 normal, right. Now that will have Miller indices, you can work it out. It is not just slightly away from 0, I have 001, I slightly tilt it, I get, you know, what would you expect, some 00 something else, 1.01 or something like that, right. But you know, so the planes do not change that gradually, right. So the planes, you know, so slight tilt angle, this becomes a very high index plane, right. So this becomes some 25, 39, 403 or something like that, right. I am just making up stuff, right. So this may not be at 89 degrees, you can calculate, right. So what is the angle between 001, actually you can calculate it, right. So 403 divided by 25 plus 29 square plus 39 square plus 403 square, that is cos theta, right. That is almost close to under root, right. Or I can make these numbers arbitrarily wrong, you know, 39,000 or something like that, right. So 2500 square, 39,000 square, anyway. So I am trying to make cos theta, value of cos theta as close as possible to 0, so that, you know, this theta can become as close as possible to 90, but it is 89.9 degrees. Okay. So that is the idea, but these planes are going to have high Miller indices, right. So as a result, if they have high Miller indices, they are going to be very energetic planes, right. So the surface energy is large of HKL planes with large HKL is not the least surface energy, right. So is actually large. Okay. Now surface energy of, I said, HKL with 100 less than for a causal crystal is less than 110 is less than 111. When will I ever come to so some what did I say 2500, 493, 100, 400, something like that. When will I ever come here, or 392? Okay. So I have to cross all these things, and this is a very high energetic plane. Okay. Now materials do not like that I have high energy. Okay. So in general, even if I do a miscut, right. So let us say I am unable to cut it exactly at 90 degrees, there is some small miscut, right. But small miscut is landing me into a conundrum that it is exposing planes of very high surface energy, right, and so that is not good. Okay. So the way a crystal actually accommodates this, and we will actually prove it again in the next class or perhaps after that, is so I do not want a plane which is like this, rather I would split this plane into a 100 plane, or so a 001 plane, let us say, and a 100 plane. Both of them have the same energy, again a 001 plane, again a 100 plane, and so on and so forth. I am going to make these terrace like structures, right. Overall I have that angle, the Miscut angle, but eventually I am going to get some terrace like structure which just exposes the 100 and 001 planes, and I am back to surface energy minimization. These planes have the minimum surface energy. Okay. So generally, I mean, you can never get singular surfaces are unstable. A slight unstable meaning a slight deviation is going to blow up your surface energies, like we saw here, right. And so the slight deviation is accommodated as terraces, right. So these terraces are so this terrace like, so always so it is good to always have what are called vicinal surfaces. So surfaces with miscut angle are what are called vicinal surfaces, as against singular surfaces which do not have any miscut angle, but that is just an idealization that does not exist. Even a small degree of miscut leads to vicinal surfaces, and vicinal surfaces have what are called terraces, and these terraces are formed so as to minimize the total surface energy. We will exactly look at what sort of planes will split into two other planes. So for example, here some very high surface energy plane is splitting up into 001, 100, 001, 100, and so on and so forth, right. So those are the, and then that forms a terraces, right. So which are at 90 degrees with respect to each other. Okay. Now why are these terraces, okay, so let me quickly show you, so for example, if I do an AFM image, right, so you can see it here on a surface, so you can actually on a surface which is well grown, well treated and other things, you can see that the color contrast, AFM gives me a height contrast, and these are the terraces, right. So, there is some height change here, there is some height change here, there is some height change here, and this height change is atomistic, right. So, in fact, you can, I am sorry, I can't see the scale bar, but this height change will be 5 angstroms or something like that. That will be a unit cell or 2 unit cells, it will be discrete, right. So, in the units of a unit cell or 2 unit cells or something like that, right. So, you can see these terraces from AFM in single crystals, okay, and these terraces come from every substrate you buy is a vicinal exposes a vicinal surface, and all these vicinal surfaces have terraces, or you can actually treat them, right. So, you can actually so if you do not have terraces because it got oxidized or whatever it is, right. So, the surface got oxidized or whatever it is, you can actually treat them, treat these surfaces. Treating means you heat them a bit, right. Let there be enough flow, and once there is enough flow, it will start reorganizing itself into these terraces, right. So, enough flow of atoms, these things start reorganizing them into terraces. Now, so is it good or bad to have terraces? Let us say, let us ask that question, is it good or bad to have terraces? In general, right. So, if I am doing any sort of growth, right, I want my atoms, these are the cubish atoms, to fall on my surface, right, and these atoms so the surface is at a high temperature, right. So, I am doing some in situ crystallization, like using pulse laser deposition, okay. So, the substrate, I will talk about it, right. So, I did not talk about it here, what is in situ crystallization versus ex situ crystallization, but I am using a technique where the substrate temperature is already large enough that once the atoms come and hit the substrate, they start moving around, right, they start looking for places to go to, and eventually so if there is a terrace like this, they can go and get stuck on the terrace, okay. So, and then once it gets stuck on the terrace, the second atom can come and get stuck on the terrace and so on, and then so this terrace itself can grow in what is called a step flow mode or something like that, right. So, the terraces can act as nucleation sites for these atoms, right. So, atoms can go get stuck, so in some sense, so terraces are useful in that sense, right. So, I will want to have a good enough terrace density, so that I will have nice growth, nice thin film growth, let us say, on substrates, okay. So, that is the use of terraces, we will come back to this in a while, but you can see that this terrace itself has some structure, it is not a single so it is not a terrace like what I have drawn, this has some lateral structure. We will actually look at various sites that come up, because I have what is called a kink position here, I have some a terrace position and all these things, right. So, it is more structured than what I just said. First of all surfaces once with a small miscut will break up into these terraces, that overall they maintain the same angle of miscut, but in general they at a very local scale they will maintain these terraces. These terraces are useful for material growth, let us keep that in mind, and so the terrace itself has a structure associated with it, right. So, let us look at the structure of the terraces, and then in the structure of the terrace there is one very good position called a half crystal position or a kink position, right. I will tell you this about more about half crystals and kinks in the next class. That actually helps us calculate the surface thermodynamics, right. So, that atoms at the kink position will be so I am going to assume that atoms at the kink position are in equilibrium with atoms that are in vapor phase. So, whenever there is a deposition, atoms come, fall, they move around, that is okay, but they get stuck at the kink position, right, or atoms get dissolved from the kink position, go into the vapor, and I am going to assume this equilibrium between the solid where the atoms are getting stuck at the kink position and the vapor where the atom has been dissociated from the kink position, right. That is the important position, that is where I can treat all my crystal growth with some kind of a mathematical nuance, okay. So, half crystals are important, and that is the structure, there is more structure to this terrace, and in that something called half crystal will come up, we will actually look at it in the next class, right. So, we will introduce a bit of so when can crystals really deposit, when can crystals not deposit, right. So, I need these sort of positions in on my surface. So, it is not just enough to have surfaces, it is so I want surfaces, but I also want some structure to the surface. One of them is terraces. These terraces form if I have a vicinal miscut, right, and in these terraces there is a substructure to it, right. So at an atomistic scale, right, so it's all very beautiful now, right. So atoms should go and get stuck onto those positions, and then I am going to do thermodynamics of that position, atoms getting stuck to that position and making bonds in equilibrium with the gaseous phase. Right. So this is the sort of thermodynamics that I look for when I look at surface thermodynamics, and this is very important. That is what tells me whether my steps can grow nicely, form films, or they will grow as nanostructures and form nanowires or whatever it is, right. So substrates are important, surfaces are important. Okay. All right. So with that, let us conclude this class. I will come back again in the next class. Okay. Thank you very much. Bye bye.